Okay, so we'll continue on. Maybe I'll just take a brief moment to illustrate why the normal approximation to the binomial works. Okay, so you could imagine the binomial being kind of like this population where we just have a 0 and a 1. Okay. So, and the limits. Okay, so you can imagine the binomial being kind of this population where you either get a 0 or a 1, okay? And so here, we can run kind of the same type of thing, all right? And here I'm going to draw a random sample. Whoops. Okay, and here with samples of size 2, we see, okay, we can get, 0 both times or 1 both times, and the average of the two could also be 0.5. All right, and then with samples of size 3, we can see, we can get these results, and as we do, it's almost like so with the binomial, we can think of this almost like kind of taking the sample mean of a bunch of draws of zeros and ones. Okay, with the binomial distribution, we often end up looking at the counts, but I could say the counts and the means are very much related in just that I would just take the number of counts or the count of how many successes I have, and I divide by the number of trials. Okay, and so those two things are innately linked, right? So if I flip the coin 100 times and it landed heads 53 times, I could say my count of heads is 53, or I could say my mean is 53 out of 100. And I get a proportion of 0.53, okay? And so here, with the binomial, with the central limit theorem, we're looking at the mean, but essentially, if I just multiplied the numbers across the bottom by how many trials I had, I would essentially get a count there, okay? And so, oops, what did I do here? I have to do replace is true. Okay. I did something wrong here. Okay, and so, as I increase the number of trials, we can see that we get things that start to look more and more like the normal distribution up into the point where essentially it becomes the normal distribution. Okay, and so this is, here again, if I look at the population, oops. It's just a 0 and a 1, a success or a fail. But after a bunch of trials, the sampling distribution of basically the average number of successes that I have looks like the normal distribution. Okay, so it's pretty much the central limit theorem applying there, but you're just treating it as zeros and ones for the number of successes. Okay. All right. So. I guess the key point of chapter 5 is that we have the central limit there, right? That we can say no matter what the population looks like, we know that the distribution of y bar follows a normal distribution centered at mu, okay? So I'll say, the key point of chapter 5 is, central limit theorem. Okay, which is basically, no matter what our population looks like, you know, as long as we have random samples of big N, with large N, we can say that the distribution of y bar is normal, okay, with a mean of mu and a standard deviation of sigma over the square root of n, okay, where the mean is the population mean, right? Okay, and so we're going to start chapter 6, which is our first kind of step into statistical inference. Okay, and we're dealing with confidence intervals. Okay, this is our first step into statistical inference, okay? So I don't know, do you guys remember kind of the idea of statistical inference from like our first week of class? Yeah, so yes, exactly. So again, the big idea is we have a population which is too big to be observed. So again, what we get to do is we get to observe a sample, and statistical inference is taking what we see from the sample and then making a conclusion about the population based on what we see in the sample, okay? Taking what we see in a sample drawing a conclusion about the population. Okay? So this is where we are headed because the population again is too big to be observed directly. Okay, and so the idea behind a confidence interval is basically this. So, you know, all of this stuff with in chapter 5 when we were creating these sampling distributions through our simulations and on the computer, we had the luxury of having this artificial population, okay, that I could just directly look into, okay? But in most of the time, we don't know the population. We don't know the mean of the population, okay? So in reality, we almost never know what the mean of the population is. Okay, and so the question here is, let's say I'm able to obtain a random sample from the population. Okay, and when we look at this random sample, the sample has a mean of y bar, okay? Let's say 103, okay? what does this tell me about the value of the population mean? Okay. So, from our sample, we can get sample summary statistics. Okay, we can get y bar, we can get the standard deviation, and we can get the sample size n. Okay, so we can get this information from our sample. Okay, we don't know anything about the population mean. We don't know the population standard deviation. We don't know even how big the entire population is. Okay, but from what I've observed in my sample, can I say anything about the population mean mu? Maybe, maybe not. Okay, all right. So this is kind of the this is the question we have, right? So this is the info we have. Okay, and we do not have population info. So we don't have mu, we don't have sigma, okay? Or we don't have, I guess, capital N being the size of the population. That doesn't even matter, but basically we don't have this stuff, all right? So based on this, can I say anything about mu? Okay. Sigma would be for like another class. In this class, we're just gonna ask like, can I say anything about mu? All right, Can we say anything about mu? What do you guys think? Yeah, it depends. That's a good answer for everything in life. Yeah. The standard deviation of the sample? We can't get the standard deviation of the population. Yeah, no, we can only get information from our sample. So I'm saying like the mean of my sample is 103. We could say like the standard deviation of my sample is 14 or something, and maybe this is a sample of size 20 or something. Okay.
Could you like reverse, like use that like the equation to get the standard deviation? We don't have you have the standard deviation from. That's not allowed.
Well, we don't have. So this is the standard deviation of the sample. Okay. S is the standard deviation of the sample, and it's not the standard deviation of our sampling distribution. We don't have a sampling distribution, right? Okay, because so your question is, can I reverse somehow if I have the standard deviation of the sampling distribution? But we don't have the standard deviation of the sampling distribution because to get the standard deviation of the sampling distribution, that requires multiple samples, like thousands of samples drawn from the population. And usually we don't have that kind of money, right? We can only get one sample. It costs us this much money to get this one sample of data. This is what we have, right? We can't just be like, oh, well, that's great. Go back out there and get me, 1,000 more samples like this, and we'll do some kind of study. I mean, there have been studies like that, and those are like very costly meta-study type things, but we don't really get to do that. So we just have one sample. We have the standard deviation of the sample, not the sampling distribution. Based on this sample, what can we say about the population? Okay, so keep that in mind as I'll try to hint at what we can do with this, I don't know, silly story example. Okay, so let's say, I don't know, someone posts this picture on Instagram, maybe Snapchat, I don't know. Well, so this will be Instagram. And what it is, it's this is my beautiful artwork here. So this will be, we're on a football field, and this is a dog. Okay, all right. So We have a picture of a dog at the 30-yard line. Dog at the 30. Okay. Hashtag where is the owner? Okay. And hashtag he is invisible. And with an invisible leash. All right, so we have an invisible owner with an invisible leash, okay? And we want to know, okay, well, the dog's at the 30-yard line. Can we say anything about the location of the owner? All right.
Not with our current data set.
Yeah, not with our current information. Okay, so I'm going to give you some more information. So some important information. Okay, so the leash is elastic. Okay, can technically stretch to infinite length. Okay, it's like super elastic. Okay, can technically stretch really far. Okay, but the dog doesn't like to get choked, okay? So, so most of the time, okay? But we also, but dog's behavior, the dog behaves in such a way that, okay, 68% of the time, he remains within 1 yard of the owner. Okay, and we will say 95% of the time he remains within 2 yards of the owner. And we'll say almost always, but not always, 99.7% of the time, he will be within 3 yards of the owner. Okay. So this is the info that I've given you now. Okay. So we see the dog at the 30-yard line, and he's going for a walk with his invisible owner on the invisible leash. Can we say anything about the location of the owner? Yeah, what can we say?
So he's probably within 3 yards.
Okay. Yeah, I mean that's a good thing. Well, yeah.
So you would make a circle around the dog, like a radius of a yard, or not a radius of a yard, like a radius of a yard.
A yard or 2 or 3 yards, okay?
Yeah. And then
Okay, so what we can say is we can say something like this. So we can't guarantee that the owner is located anywhere because technically the leash can stretch very, very far, okay? But we can say something like, I am 95% confident that the owner is between, and so we're just going to assume this kind of this one-dimensional thing is between 28 and 32 on the field. Okay, does that feel reasonable, like a reasonable thing? Okay, and or I could, I could be less confident. I can say, I'm 68% confident that the owner is between 29 and 31. Okay, or if I wanted to be more confident, I would have to extend that. Okay, I could say, well, I'm 99% confident the owner is between 27 and 33 or something like that, right? Okay, could the owner be at 34? The owner could be at 34, right? But what would that mean?
Can only say.
So the owner could be at 34, but that would mean that this picture was taken at one of those very rare occasions where the dog strayed very far away from the owner, okay? Contrary to his normal behavior, okay? So the answer would be yes. Yes, but we would be surprised that means the photo was taken at a strange time when the dog, strayed far from the owner. Okay? Which is unusual given the known behavior of the dog. Okay, so why did I tell you this? So the idea here is that we can see the dog, and the dog can be thought of as our sample mean y bar. We are allowed to see where y bar is located, okay? We don't know where the location of the owner is. We don't know where the population mean, mu, is, okay? But where the dog can go is technically determined by where the owner decides to stand, right? Because the dog's on the leash, okay? But because we know the dog's on the leash and we know the behavior of the dog, if we see the dog located at 30, we can then say, well, the owner has to be somewhat nearby, okay? And so in the same way, if we see y bar located at a certain place, we can say the owner should be nearby. Or, I mean, sorry, not the owner, the population mean mu should be nearby, okay? So where's the owner? The owner can be thought of as population mean mu. Okay, can I flip the slide, or are you still writing here? Okay, so so we can say y bar, the sample mean, follows a normal distribution centered at mu. Okay, that was the central limit theorem. Okay, so when we see y bar, okay, we know that mu should not be too far away. Okay, and in fact, we know that about 95% of the time, y bar will be within 2 standard deviations of mu. Okay, what is the standard deviation here? The standard deviation, it's the standard deviation of our sampling distribution, right? This is the, because we're talking about the distribution of y bar. So this is, I'm sorry?
Never mind.
So this is the standard deviation of the sampling distribution for y bar, right? Okay. 2 standard deviations of mu, and so that standard deviation of the sampling distribution of y bar is sigma over the square root of n. Okay. There's instead of saying the standard deviation of the sampling distribution of y bar, we often give this the name the standard error, or SE. Okay. So we can say, in fact, we know that about 95% of the time, y bar will be within 2 standard errors of mu. Okay. Is that okay? All right, and so from this, okay, we can create a quote loose, well, we can create a, I'm going to just call this a basic confidence interval. And say something like, I am 95% confident that the population mean mu is between, and it's going to be y bar minus 2 times sigma over the square root of n, and y bar plus 2 times sigma over the square root of n. Okay? So this is, basically when I said, I'm confident that the owner is between 28 and 32, that's basically all I was doing. I was saying, the dog was located at 30, and, I say within 2 yards or something like that. Okay. Does this feel okay? Kind of how we got here? Okay. There is a problem, though. Okay, and do you guys see the problem?
I thought you said before that we didn't have the sample distribution.
We don't. That's exactly right. So the problem here is that we're saying I'm 95% confident that the population mean mu is between 2, and then we're saying sigma over the square root of n. Okay, but we don't have sigma, right? We don't know. So this would be nice to say, but we don't actually know sigma. Okay, so there is a problem. We do not know what sigma is, okay? And so, there is we do have n, we do have y bar, and we do have 2, okay? But we don't know what sigma is. So what do we do there? So we don't know the population standard deviation. What seems like a reasonable thing to do? Like, if you had to, jerry-rig something together, you're stranded on the island, you got to try to figure something out. You don't know what sigma is. What seems like a reasonable thing to plug in for sigma? Like if we had to... Okay, well, I think a reasonable solution is to use the standard deviation of the sample. Okay, so even though we don't know the standard deviation of the population, it seems reasonable to use the standard deviation of the sample, right? Like the mean of the sample should give us an idea of what the mean of the population is, as the standard deviation of our sample should also give us kind of an idea of what the standard deviation of the population is, okay? So, a reasonable thing would be to use the sample standard deviation, S, as an estimate of the population standard deviation sigma. Okay. And if you read up on the history of statistics and stuff, this is what people did, okay? But then people started running into problems because they were not using the actual population standard deviation sigma, and they were using S instead. So the story goes to the Guinness Brewery in Ireland. Okay, there's a guy in the quality control department, Gossett, and he would test out these batches, and he would say, based on my calculations, we got to throw this batch out. But then they would do further testing, and they're like, no, man, this thing is fine. This beer is fine. There's no problems, okay? And so he went back and he said, I think I'm running into a problem because I'm basically using S instead of sigma here. And so, but he didn't fully understand the math, and we're not going, and it's kind of beyond the scope of this course, but basically, after doing this impressive kind of study of just like a bunch of manual calculations by hand, he realized, oh, I have to kind of I need to include kind of like this compensation factor for using S instead of sigma, okay? And that led to the development of the T distribution, okay? So using S instead of sigma, okay, introduces a little extra uncertainty. Uncertainty into the mix. Okay, so to compensate for this, we will adjust the number 2 to a different thing, okay? The value of 2 to something else, okay? Okay, based on what we call the T distribution. Okay, and this was known as student's T distribution because Guinness Brewery didn't want these research papers to be traced back to them, so they told their employees that if you're going to publish research articles, you got to publish it under a pseudonym, and so Gossett chose the name a student, and so it became known as student's T distribution. Okay, it's interesting, right? So student's T distribution. This was like early 1900s. Okay, so statistics, compared to like physics and stuff, it's a relatively young study. Okay, or compared to algebra, which is invented by the Arabs. It's very old. So okay. So anyway, oh, do you know why algebra is called algebra? Or no, now I don't remember. The story was why we use X for everything in algebra, and it was this is like another story. Outside of this, I'll find the TED Talk and post a link. Okay, so students T. I like this kind of stuff. Maybe. All right, so this introduces a little bit of uncertainty. So we're going to use the T distribution. Okay, so basically, now our confidence interval goes from, we're going to say y bar minus, and to indicate the value, instead of 2, I'm going to call it t star, okay? And then instead of sigma, we're plugging in s divided by the square root of n to y bar plus t star times s over the square root of n, okay? Or a lot of times, just we combine the plus and the minus. We just say y bar plus minus t star times s over the square root of n. Okay. So t star, our choice of t star actually will depend on our sample size. Okay, and I think this makes sense. Because if you have a big sample, the sample standard deviation should be pretty close to the actual population standard deviation if you have a huge sample. Okay? On the other hand, if you have a very small sample, like only 3 or 4 things in the sample, then the standard deviation could be wildly different from the population standard deviation just because you're basing it off of a very small sample. Okay, and so our choice of t star takes that into account in this thing called degrees of freedom. Okay, so t star depends on degrees of freedom. Okay, and for confidence intervals, df is equal to n minus 1. It's your sample size minus 1, okay? And basically what happens is when df is big, amount of compensation is small. To t star is small. And then when df is small or low, compensation to t star is big. Okay, so t star depends on the degrees of freedom and also our choice of confidence level. Okay, so back when we were talking about the dog, I said I can say I'm 95% confident that the dog is between 28 and 32. But likewise, I could have changed my confidence level and said, or not the dog, that the owner is between 28 and 32. I could have said I'm less confident. I'm only 68% confident. But then I would have said that I'm only 68% confident that the owner is between 29 and 31. And if I want to be really confident, I could say I'm 99.7% confident that the owner is between 27 and 33. Okay, so our choice of confidence level will also determine what kind of factor we should use there. Okay, so if you go to your reference tables, the third page should be, or the second sheet should be table for critical values of students' t distribution. Okay, and here,
Makes more sense.
what's that?
That title makes more sense.
Yeah, so it's students' t distribution, yeah, so reading for your own enrichment, you can look up students' t, William Gossett, I think, and the t distribution and its history. So here we will look at, what do we use for 95%, okay? And, we could go anywhere from 99 to 60% or something. So we can see at 95% confident, if I have an infinitely large sample and have infinity degrees of freedom, my value would be 1.96, okay? And this, so it's not plus or minus 2, it's actually plus or minus 1.96, and that comes from the normal distribution, because if you're looking for the middle 95% on the normal distribution, we would have 2.5% in each tail, right? 2.5% on the lower end and 2.5% on the upper end. And if I looked up where 0.025 is in the normal table, 0.025, that corresponds to negative 1.96, okay? And then on the positive side, you know, it's symmetric, so it's the same. 2.5% is there. So that's where we're getting that. Okay. But anyway, so around for 95%, your values are close to 2, and you can see that as the number of degrees of freedom decreases, instead of 2, we use slightly larger values. So, you know, 2.08, 2.1, 2.3, all the way up until you have, you know, when you have very small sample sizes, you have very large compensation factors, right? 2.7, 4.3, or things like that. Okay, and they get crazy huge when, you know, if you want to be really confident and things like that. Okay. All right. Yeah, and again, if we want to be more confident about, quote, catching the location of mu, we have to make our interval wider. Okay, so we use, instead of 2, we use larger values like 3. And if we're willing to be less confident, we can use smaller values here. Okay, so there's kind of a trade-off between having a wide interval, which is generally less useful than having a narrow interval, right? Because I could say, you know, whatever question you ask me, you know, what's the average whatever, I can say, oh, I'm 100% confident that the answer is going to be between negative infinity and positive infinity. Okay, that's not going to be very useful. You know, what's the average lifespan of people on Earth? I could say, oh, I'm 100% confident it's between 0 and 300 years. You know, these are not useful values, right? And especially if you want to make comparisons between, you know, one group to another group, it's not so helpful if you're like, oh, for one group it's between 70 and 90, and the other group it's between, you know, 71 and 92, like, where, you know, it's not, these are not handy things to have. So you want to have, you know, kind of have a narrower interval and things like that. But the trade-off is, if you're going to make your interval more narrow, you're going to be less confident about that interval. Okay, so let's try this out. Let's do a little problem here. Okay, so we'll say you take a random sample of, what are we taking a random sample of? Anything? What? Random sample of hummingbirds? Okay. Yes. All right. Okay, so we obtained some random samples of hummingbirds. I don't know how we did, but we managed to do it. Okay. Random sample of hummingbirds, and we want to know, you know, what is the, you know, and we weigh them, right? Okay, so we get the average weight. We'll say maybe we have 10 hummingbirds. Okay, we got 10 hummingbirds. I'm going to ask Google, what is the average weight of a hummingbird? I shouldn't hear me. What?
Hummingbird has a weight of 0.056 to 0.071 ounces.
That I have no idea what that means. Okay. That sounds very light. Yeah. Okay. They're very, very lightweight. Okay. So we'll say 0.06. I'm completely making this up. 0.63 ounces. What is that in grams? I can't even comprehend this. Okay, that's like 4 Cheerios, right? Okay. So the average weight is 0.063 ounces. Let's say the standard deviation is like okay, we'll say 0.08 ounces. Okay. All right, so we'll make a 95% confidence interval for the average weight of hummingbirds in the population. Okay, I'm going to pause the video here. All right. Okay, so all you do is you just plug in 0.063 for y bar, plus or minus. Okay, so our degrees of freedom will be 9, right? So we look up 9 at 95% and we get 2.262. And we plug in s 0.008 divided by the square root of 10. Okay, so we're just on the scale of really small things that have hard to understand meanings in real life, but 0.008 divided by the square root of 10. Okay, so I get 0.063 plus or minus 0.0057. Okay, and so this gives me 0.063 minus 0.0057. So on the low end I will have 0.0573, and on the upper end I just do a plus and I get 2.0687. Okay, and I would say something like, I am 95% confident that the average weight of all, and apparently this was bee hummingbirds, of all bee hummingbirds in the population is between 0.0573 ounces and 0.0687 ounces. Okay. All right, so based on this statement, let me, so I'm going to just cut and paste this. You know, someone can ask, you know, do we have evidence against the claim that the average weight is 0.069 ounces? Okay. And what do you guys think? Yeah, so our answer would be yes. Okay. 0.069 is outside of our interval. So I am confident. So we say we have evidence against the claim. Or so we say we have evidence that the average weight in the population is not 0.069. Okay? On the other hand, so same question, ... against the weight. Do we have evidence against the claim that the average weight is 0.068 ounces. Well, so
Do we say yes?
so here we say no, okay, and so we say no, 0.068 ounces is inside our interval. Okay, so it is a plausible value for mu, or the the mean weight of the population. Plausible value for mu, the mean weight in the population. Okay. All right. So so I don't know how comfortable this sits with you. So basically, we just say if the value is inside our confidence interval, it's a plausible value for the population mean mu. And if it's outside our confidence interval, we say, I mean, technically it is technically possible, but we have, our evidence points against it, and we'd say we have evidence against that claim, okay? Is that okay? Yeah, question.
So if something is like on the edge,
Uh-huh.
really close to the end of the confidence interval,
Yeah.
versus like in the middle,
Uh-huh.
is one more likely, is the one in the middle more likely? Or is it just random?
Yeah, so the word likely is not the correct word to use, okay? And I'll get to this, okay? So the way the confidence intervals work is basically it's this harsh, if it's inside, it's a plausible value, we don't have evidence against it. And if it's outside, while it's technically possible, we say we have evidence against values outside of the interval. Okay, so it's kind of, as far as the interpretation of the confidence interval goes, it's kind of black and white. Okay, but what we do have, all right. So if we just flip back to the formula for the confidence interval, our confidence interval depends on T star. Okay, and so if instead of saying I wanted you to make a 95% confidence interval, if I said make a 96 or a 98% confidence interval. So let's say I said, make a 98% confidence interval. Instead of 2.262, you would have used 2.821. And 2.821, if you use that, this number would be larger than 0.069, okay? So if we bumped that up, we would have gotten, basically 0.069 would have fallen inside our range, okay? Or on the other hand, if I decreased my confidence level to like 90% or something like that, then 0.068 would fall outside of our interval, okay? And so the interpretation now becomes, you say, at the 95% confidence level, I do not have evidence against 0.068 ounces. Or you can say at the 95% confidence level, like, I have evidence against 0.069 at 95% confidence, okay? But, when we're talking about values on the edge and boundary, we can say, at 95% confidence, I don't have evidence against 0.068, but at 90% confidence, I do, okay? And so there's this question of that if you're willing to be less confident about the statement you're making, you can start throwing away more on the edge, okay? And then there's, again, just this balance of how much of these edge cases are you willing to throw away, and how much confidence do you want to maintain in your answer, okay? And so that's what we have, in dealing with uncertainty, because at the end of the day, we're trying to make a statement about the population based on just a sample we see. All of our statements are just based on kind of this assumption that the normal distribution or the central limit theorem works here, okay? And so, over here, there was an implicit assumption when we said we're going to make a confidence interval. The assumption here is because I have a fairly small sample, I'm assuming that hummingbird weights in the population are somewhat normal. Right? If they're not perfectly normal, they're at least unimodal and symmetric, and that our distribution, our sampling distribution, does obey the central limit theorem. So there's a lot of kind of little things working on in the background that most of the time we can kind of get away with, okay? You know, when we're talking about hummingbirds, it's reasonable to think that the weight of hummingbirds follows a normal distribution, I think, okay? But if what we were talking about is, I don't know, income or even human weight, where, you know, they're both skewed, you know, our confidence intervals would not work as well. Okay, so there's a trade-off between the width of our interval and their corresponding interpretations. And our level of confidence. Okay, so we can have narrow intervals, okay, generally desirable, okay, if we are willing to be less confident. You know, our statement, which is undesirable. Okay, or you know, we can, you know, we have wider intervals if we want to be more confident. You know, the other option, if you want to have a more narrow interval, the other option is to gather more data. Okay, and that will give you the other option. Other option for a narrow interval. Other option for a narrow interval. Okay, let's see here. Okay, so I want to say a few. So far what we've said is the correct interpretation of the confidence interval. So let's say our interval, let's just say for some interval goes from, I don't know, 70 to 73. Okay, 95% confidence. Okay, so here we would say, you know, the correct interpretation is, we say I am 95% confident that the population mean mu is between 70 and 73. Okay. All right, so here's a question. Is this a correct interpretation or not? There is a 95% probability or 95% chance that the population mean mu between 70 and 73. What do we think? Is this statement correct or not correct? Okay, so some people are saying no, some people are saying yes. So if you say no, why are you saying no?
Earlier somebody said something about probability and you were like, oh, that's not quite right.
Okay, all right. Okay, okay, so,
Yeah.
well, okay, so
We're measuring confidence, not.
we are measuring confidence. All right, so again, this is a frequentist classical approach to probability. Okay, if this were a Bayesian class, then this would be an acceptable interpretation. But as far as the frequentist view goes, this is not. And the reason why is this. Well, maybe I'll illustrate. So I'll take one of my quarters here. Okay. And I'm going to ask you it's not a trick question. What is, if I flip this coin, what is the probability that it will land heads? 0.5, right? Okay. All right. Okay. I'm going to ask you, what is the probability that the coin landed heads? Okay, so you guys still say that. Okay, now watch this. Okay. Okay. So and I'm going to ask the same question. What is the probability that the coin landed heads?
With you looking down, is that a trial?
It's not a trial. I'm looking at it. I know the result of this coin flip, and I'm asking you, what is the probability that the coin landed heads? 0. Okay, and so the truth is from the frequentist point of view, the last two questions, after I flip the coin, it's a nonsense question. It does not make sense to ask about probability for an event that is determined. Okay, the coin has landed. There's no uncertainty about it, so that no longer makes sense to talk about probability. Okay, so it either landed heads or it didn't. You guys don't know the answer. So once the coin has landed, it no longer makes sense to talk about probability. All you can say is, I am 50% confident that it landed heads, or I'm 50% confident that it landed tails. Okay, but we can't talk about probability. And in the same way, we believe that the population mean mu is a fixed value. Okay, there's no uncertainty in here. If we could freeze time right now and observe the population, we would get a value for the mean mu, and that's some number. Okay, there's no probability associated with it. It's some number mu. Okay, we don't know what it is, but it's fixed. There's no uncertainty. So it doesn't make sense to talk about probability. All we can say is that we are 95% confident that our interval manages to get at the this value mu, but there's no uncertainty here. Okay, so this is wrong because there is no uncertainty in mu. Okay, it is a fixed value. Okay, we don't know what it is, so all we can talk about is confidence. Okay, it landed tails, by the way. As far as, but in the Bayesian probability probability is a statement of belief. So when you talk about probability that it landed heads, it's your belief that it has landed heads, and that would be allowed. And so so it's a little bit different. Okay. We don't need to get philosophical about all of it, and whenever we talk about probability, I wonder, what is truly random, right? Because the coin flip is it's a result of the rules of physics, right? Like how much angular momentum there is, and how strong gravity is, and how bouncy the surface is. And so, is it random? Not really, right? Okay. Okay. Other interpretations that are wrong. Okay, would be I am 95% confident that future samples will have a mean between 70 and 73. Okay, so it says nothing about future samples or future observations, future samples or future observations. So the confidence interval says nothing about that, or that 95% confident that that the data is between 90 or so these are also wrong. It's also wrong to say 95% of data is between 70 and 73. Or or even, I am 95% confident that the sample mean okay. And this last one is wrong because we know what the sample mean is. We've observed it. Okay, so that we are 100% confident that the sample mean is this exact value. Okay. And then if that's the case, we just say the sample mean is this value. Okay, so these are all wrong interpretations. The only correct one here is we make a statement of confidence about the population mean. Okay, and that's what we can say. Okay, so we will stop there, and we'll see you guys next week. Have a good weekend.